Final, or well, probably final installment, we are going to revise our definition of the state monad so as to the state monad with errors to include what is perhaps the most powerful extension that we're going to build. And this extension is not only powerful, it's also something that's traditionally very difficult in computer science and relatively underrepresented in modern frameworks and libraries. We're going to build soft threads or coroutines. The idea is that a coroutine is basically a stateful computation. It has a state S, it can produce errors E, and it hopefully produces at some point a result of type A, obviously paired with a new state. But the coroutine is built to represent long-running operations that we do not want to simply get our process stuck. And we don't want the user to simply look at a stuck process while it's running some slow computation, or animations, or interacting bots, all things that need to be able to include time in their long-running process. So the idea is that when we have a coroutine, we give it a state. So we take a state, the current state, and we say, okay, here's the state, go do your thing. And right now what we have is very eager, so it goes right away until it computes until it gets to the error, or until we get a result, which is the value and the new state. But we don't want to get this right away. We want to say that the coroutine, well, the error we want to be able to give it quickly, but the result we want to delay it. So we either get, indeed, this result. I'm going to leave the result to the leftmost, or a pair of the new coroutine, which represents the rest of the application, and the new state. Okay. Now I'm going to format my type properly. Yes. So let's see. Okay, that looks decent. Okay, so when we put in the state, it might be that we get an error right away. If we get the error, that's good, because the coroutine says, okay, you gave me a state, I've done what I could, but this is all I get. Or we get, well, a new coroutine that says, I'm not done, and this is the rest of my own process. Or paired with a new state. So it says, okay, I'm not done, but what I can tell you is that this is the state I have until now, which is not the final state of the application, but that's okay, because we want the A as a result, but we accept the fact that this is the new state. Or the coroutine says, I'm done, and here's my final result A and my final value S. Okay. It's also interesting the fact that we were kind of forced to indent this properly, because we are doing data-driven design. So we start by modeling our data and our processes in this case extensively, and when it's modeled, the rest almost falls into place. Now I'm going to change our definition. I'm going to say that, well, our state, we turn it into coroutine. You know what? I'm lazy, so I'm going to keep this as state. I'm simply going to say that F is a coroutine SEA, and I'm just going to change this rename, yes, to coroutine. That's better. Okay. Now, obviously, all sorts of things are going to break. Now, this is not the function, but it's co, SEA. Co stands for coroutine. Well, you know what? I'm going to call it co-fun. Yes, that's even better. So the function of the coroutine, obviously state from fun takes as input co-fun of SEA, and there we are. So state from fun, which and fun from state, they are exactly the same, because they don't do anything special. They just wrap the result of they extract the co-fun from the coroutine. That's super easy. Or they add the then operator next to the co-fun for ease of use, because we want to be able to say monad.then, etc. Mapping is the first place where we get a bit of a challenge. Well, we can imagine that map state is well, we have to rename these things now because this is not state from fun, but this is coroutine from fun, and map state is obviously map coroutine. But you can imagine that here, map coroutine, if we go back and look at what this does, now we can run the function and then we get this result. Now all of these things are functors. Also, well, the function is kind of a functor in the return type, so that's also cool. So we could say that in order to map something that is built as a functor, we simply map all of its components, but there is a problem. The problem is that here we have the coroutine itself. So here we could say, okay, map either, then there's going to be map either, then there's going to be map pair, then there's going to be map pair, and here, what we're probably going to get is map coroutine again. So in this sense, we have the usual, so map coroutine is relatively easy to build, minus the sort of elephant in the room that when we come to this bit, in order to map this bit, we have to call map coroutine recursively. So let's try. I'm going to just try, you know, to follow this now because, well, at some point, and you also know that this is probably going to break many times. But let's see if we can do this relatively easily. So we have either, pair. Okay, so let's begin with a map either. And the left side of the map either is going to be, again, map either. And let's say also null and null, because the right side, that's quite easy, that's E, and that has to stay E. I'm going to give all the type annotations I possibly can. Are we missing brackets here? Are we still missing brackets? Okay. Yeah, I don't like that many errors. Oops. Okay. Now, this map either, so we've taken care of this either, we've taken care of this E, and now we have to run this map pair. Now this map pair is relatively easy, we have it already. We know that function f is capable of turning A into B, and the S we keep exactly the same. So there you go. And the system is happy, but now we have to map this coroutine here, this pair here. And this is going to be map pair, and be mindful of the fact, let's begin with our usual null exclamation mark. Now let's see how much it knows. Now that's quite interesting actually. It knows that L has to go from a cofun SEA into a cofun SEB. And R has to go from S to S. Okay, so the R, that's easy, that's IDS. And here we now have to turn a cofun SEA into a cofun SEB. How do we do that? Well, we have coroutine because that's exactly what we need to do. We have to turn a cofun SEA into a cofun SEB. Let's see if we can, first of all, define map cofun. Map cofun. And let's say that this is almost the same, but instead of coroutine, these two have to be cofuns. And what is this going to? Oh, too many equal signs. What is this going to be? Let's say this is probably going to be map coroutine. Oops, map coroutine of SE. It's just the generic parameters of F. But map coroutine, obviously, well, it takes as input the wrong thing. So let's define our function that takes as input the cofun, and then we call f on, well, not cofun, but we can extract the function from the coroutine via fun from state, and we give it the cofun, and then the result of this, we encapsulate it. No, sorry. No, that's the opposite. Yes, let's go from fun, and then the result we encapsulate with fun from state, and I'm going to change the name in a bit. Yes, okay. It looks happy. Missing a bracket. Cool. Okay. And I notice now that we didn't rename this, so fun from coroutine fun from co. Yes. Okay. Cool. Now we have this. Well, let's also make it a little bit prettier if possible, because this thing does first map coroutine and then it applies co from fun. So we could try then fun co from fun, and we apply co fun to this. No, it is unhappy. You know what? I'm not going to fight this particular dragon here. I'm going to accept that. I'm going to accept this for the moment, because far more interesting. So map cofun is now exactly what we need on this side of the pair, because map cofun with the right S and E should be just what we need. Well, let's see. So it wants on our, oops, let's see what the type error is. Oh, yes, obviously. And now we have to call it with F. Yes, because map cofun obviously needs to know how to turn the A into B, because that's obviously the payload of map cofun. And there we go. Okay, so that's map either. And notice that, and I do really like this. Notice that if you look at this and this next to each other, they are kind of the same. Look, the either, the type definition, became map either. The other either became also map either. The pair became map pair. Now at some point we don't know what A and S are. Actually, S we know that it stays the same, so you could have guessed this. And the other pair also became map pair. So you see that indeed when mapping a composition of functors, well, you compose the mappings of the individual sub-functors that you are composing together. That's actually pretty powerful. I'm going to delete this because we don't need it, but there is a one-to-one correspondence between the composition of the mapping of the composed functor and the composition of the mappings of those functors. But we will get to that later on. It's now time to move on to the next operator, which is probably the simplest of all, which is unit state. Unit state is the simplest of all because we already have an A, we already have a state 0, and we simply have to embed this state 0 into, now if we go here, it's left, and then left again, and then the pair. So we have, without further ado, inl of first, and first is x, so the value of type A, and the second is S0. Let's see if we can try. Oh, come on. Oh, yeah, okay, I'm not gonna fight against this one. Now, this would sort of make sense, but the type inference is now, the type inference can't follow that deeply. I hope that when TypeScript fixes this, that we'll be able to greatly enjoy the benefits of deep going type inference. But it is, oops, wrong name. It is what it is at the moment. That's the price of being cutting edge, isn't it? Okay. Join. Ooh, join is terrible. Now, let's begin by renaming it join coroutine. I am going to take a horrible shortcut here. Then we try to make it prettier. I'm not going to attempt the composition yet, because as you can imagine, we are going to have to call join coroutine ultimately after having reached the nesting, because in the nesting we're going to have the nested continuations. But for the moment, we have a state 0. So now let's begin with just the normal calls. What we want to be able to return is indeed the result of this coroutine, which is built by recursively flattening the result of x. First thing we can do, and that's the easiest because that's kind of implied, we can call x.f over S0. What do we get? We get the first either. Now I'm going to go back to plain old ifs. We check the kind. If the kind is left, what do we have in the value? Then we have the left side, so we do not have the error. Okay, that's the most difficult case, and we're going to have to drill down in that result. But if that's not the case, we can simply return inr of temp1 dot value, because that's just the error. Temp1 dot value, oops, because temp1 dot value is an e, and so by calling inr, and we're simply forcing, well, we're rebuilding the outer either by putting the error on the right side. I think we could also return temp1, but well, yeah, I mean, that's better. Because temp1 doesn't have the correct, that doesn't really have the correct type. I mean, the data flow knows that this is what it is structurally, so I can return it because the left side is ignored, but I don't like it because temp1 here has a type that's really not compatible to what we should return here. So I'd rather that this inr knows exactly what the proper type is it is to build, so it feels less hacky. But again, it's really a matter of preference. On this other side, on the other hand, well, we have v, and v is either, oops, it's either the result, which contains the coroutine inside, or it's the pair of the continuation that is ultimately going to return the coroutine. Okay, so what do? We check what v is. If v is left, otherwise, and again we return null. Okay, so if v is left, then what do we have here? We have something that's getting close to a result. Let's take a look. Temp2, that's v dot value. No, you know what? Let's use better naming. Let's call v temp. Oops, because v is really supposed to be temp2 here. Yes, okay. So what is temp3 now? Temp3 is, well, the result, which unfortunately is a coroutine, and s. Now remember that, well, this coroutine and this s are very close to what we want. So we could simply try to say what happens if we take temp3.first, which is the coroutine, and apply temp3 and apply it to temp3.second. What do we get? Now we get the return side of a coroutine, and we might actually just return it. Why can we return it? Because what this code from fun is what this fun is supposed to do is we're supposed to build this function that takes as input s and returns, well, this thing here, which is the right side of the resulting coroutine of SEA. And this right side is indeed either pair AS, pair cofun SEAS. And the most important thing you have to notice here is that, well, this is simply a coroutine in A and S. It's a coroutine in A. So that's cool. And temp4 is now the right side. So temp3 is already the coroutine in A. That's what we want. We've gotten the coroutine in A. And what we do is we simply, well, take the first step of that coroutine and we get temp4, which is the right side of that coroutine SEA, and that has already the right shape, so we can just return it. Okay, now on to the property monster, which is the recursive bit. Property monster is temp5, and the property monster is, well, the pair of okay, now that's the problem. So we can't get to this coroutine SEA. That's the issue. We cannot. Because this coroutine SEA is inside the cofun, and now we should have to put the S inside this. Oops, we should put this S here inside this cofun here, but then we get another either with inside an either, and so on. So what we should do with this is we should call join coroutine on whatever comes out of this. The problem is again that coroutine doesn't work with cofun. It works with coroutine of coroutine. So let's turn this into a pair of coroutine of coroutine. So we have to turn this cofun into a coroutine. It's not very difficult because we know how to turn a cofun into a coroutine. We have co from fun. Okay, so temp6 is going to be map pair co from fun id over s. We probably will not just get away with this. Yes, we have to specify exactly what we have to transform our pair into with type annotation. So let's go to map pair. Map pair, it wants, I don't remember what map pair really wants. It wants AB A1 B1. Okay. So this is the input. And the output is supposed to be a coroutine SEA. Yes, and now magically the compiler error is gone. Okay, so temp6 is now a function that takes as input, hey, this pair cofun coroutine S into pair coroutine SE coroutine SEA. And this is very important now because this thing here is what we can run join coroutine on. Okay, so now, you know what? Now I'm going to build temp7, and temp7 can map the coroutine of coroutine into a single coroutine SEA. And you might be wondering, hey, how do we do this? Well, we know how we do this because that is exactly join coroutine. Ooh, okay. Then temp8 is going to be temp6 followed by temp7, and temp8 takes as input, well, this monster that we had into, that's actually quite close to what we really want to have. So now we can run temp8 with temp5. So temp5 is the thing that goes into temp8. Let's simply run it. Let's pass it temp5. I'm always kind of scared that when I end up putting something like temp5 into this, that I'm going to get a compiler error because my brain is kind of at its physical limit now. So let's see what temp8 is. Okay, now temp8 is a pair coroutine SEA-S. And this is finally very good news because we want, well, a coroutine SEA is very close to what we want, but because we already claimed the state, because we need the state to bootstrap the whole process, well, now we can't really just return this coroutine, because we wouldn't know what to do with this state. So we have to return the right end of this coroutine, which is what happens when we apply this coroutine to S. So temp9 is temp8 first, F of temp8 second. And temp9 now is the right side of the coroutine SEA. And that's temp9. Okay, I am now going to try to merge some things, and I'm also going to give up very quickly if this doesn't work. So I can live with it. I can almost live with this code, you know. At some point you have to make some choices in life. So then temp7. Okay. And oh, by the way, now this is something we actually can do. So temp8 it's our pair. So well, we have the apply function. Come on, let's not be monsters. So let's say that instead of this pair of coroutine SE, so instead of this coroutine, let's say that at this point we want the cofun. And so instead of just doing join coroutine, let's say that after this, I also would like fun from co. Oh no, that's a pity. No matter. Then we go for another. Then that's that's not a problem. That's never killed anyone, right? So then we map again. and what we did get here was finally the coroutine SEA and S. There you go, and we want the cofun SEAS, so this function here has to be co from, oh, sorry, the fun from co. Isn't it happy? Brackets, yes, okay. Now temp8 is a pair of cofun SEAS, and cofun is just a fun. So now we can simply we can just say, and now apply these two things together. So we have apply, and apply just takes as input temp8, and well, it simply calls the first argument, which is sorry, it calls the first item of the pair onto the second. So that, well, that's cleaning things up. You could also say, but then you know what? After you have this, just apply. And now temp8 is exactly what we needed. Yes, there we go. And now we can just return all of this on top of. Ooh, no, it's broken something. Huh? That is puzzling. Wait a second. So if we just return temp8, it should kind of be the same. Oh, okay, the JavaScript weirdness. Okay, then we can remove this. And you could imagine that, well, all of these ifs, they would become probably some map eaters, or much more likely this new variation which we built last time, that is collapse eater. That's okay. So they're going to be a mix of map eaters followed by collapse eaters, which is okay. But you know, I don't want to go too much overboard. Oh, by the way, I just noticed that this is also something that we could very easily fix with this map coroutine followed by apply. You know what? Let's do it. So let's say that f is this mapping here, and then let's give it another name. Let's say this is temp5. Temp4 is calling f on top of temp3, and temp3 is indeed our pair of coroutine SEA, and temp4 is the pair of cofun SEA. But then if we also apply this, then temp4 simply becomes the thing we want to return, so we can simply give it back. And now we're simplifying stuff. Let's apply it right away to temp2.value, and now we can return this. And you can slowly see it happening, because now I know that this is the function I have to apply to the left side. This is the function that I have to apply to the right side, and I have to join this, and then I have to simply join these two things because they return the same. But maybe we'll get back to this later, because at some point it's just a matter of style. But I really want you to see that this is all very much just functorial, recursive functorial processing with some cherry on top. Okay, so now that's join coroutine. Then now we can rename this symbol, and we call it then co. And well, notice that this comes as always for free. Why does it come for free? It comes for free because indeed, again, then or bind is just a combination of map and join. So, well, this is an operator that is, I've also had my share of attempting these things in my young years as a programmer, and I would just try to build a monad for languages like F#, where you really need this operator with this signature. I would try to build it by hand, and well, this is terrible. Well, terrible. This is quite difficult, and join is marginally simpler because join is just kind of fancy mapping, and then obviously the combination. Okay, all right. Now we have our old program with our sort of fake memory. Obviously, we have our special units here, which are these utility functions that can produce the proper errors. And wait a second. So to produce an error, I think it's inr of inr. Oh, I've broken it. No, I've broken the other side. Inr of inr. Yes. Oh. Or not. Now let's see what we're dealing with. Let's see which one of the, so the return side, so unit coroutine is inl of inl. Okay, so that side should be correct. Let's assume that the other side is the one that might have problems, so let's just give null exclamation mark back. And we're missing a bracket. Okay, cool. Okay, so that was indeed the case. So let's see. Oh, maybe it was just a bracket problem. No, it wasn't. Why are we never so lucky? Where's the error? Let's see. The error is... oh, wait a second. The error is to the right side of the first iter. So actually the error is just a single inner. Yes. Oh, that was a bit silly. Oh, there you go. I have no idea what went wrong. Then probably brackets. Okay, that's life. That's forgetting a variable, if you remember from the previous video, where, well, when we have the successful case, we just had to add an inlet, but the right hand side obviously has to remain the same. And I see that there is something else wrong. Oh, yes, obviously in the try catch, I guess this just needs another inlet, right? No, let's find out also here what went wrong. Now let's go find out what went wrong here. So for building try catch, our goal is to run the coroutine, and then in case of error, we want to simply we want to activate the catch mechanism, and the catch mechanism is going to be invoked and produce the new coroutine as we is going to produce the new coroutine that, well, tries to continue its job to recover from the error. Okay, so obviously we run the body. We run the body, and what do we pass it? We pass it as 0. And what we get here is, well, the usual either, where on this side, this is what we just want to continue with. That's if we find left of left, then we're happy. This is the final result, and so we simply just re-encapsulate it in left of left and we give it back. If we find this side, we're also happy. But if we find, because we know we just run on error with the old state, and that's also good. If we find this side here, what do? We recursively just continue, because if we get this, it means that the coroutine is not done, so we don't know whether or not we have a result or we have an error. So we simply continue. We simply have to say, okay, you know what? Then try catch on this cofun. So let's do this. If temp1 dot kind is left, you know what? I'm going to go for the easy case right away, and temp1 dot value dot kind is also left. Well, then in this case I have temp1 dot value, and what's temp2? It's a pair of AS. So you know what? I simply return inl of temp2. Should be happy about this. Yes, it is. Okay. Otherwise, if I'm on the other easy case, temp1 dot kind is right, then what I have is temp1 dot value being an error. Okay, cool. So I can simply call on error on temp2, again happy, and temp3 is a coroutine of SEA. Then I can run the coroutine. The coroutine I got, that's temp3 dot f. I just run it on what? On the initial state as 0. And what do I get? Well, I get the whole either thingy, which is the first step, because now we have to forcibly take the first step on error, and it's okay to give back the old original state as 0, which is very interesting. It also means that our interpretation of coroutines kind of undoes everything the body has attempted So this is also subtly a transactional system that undoes whatever the body has done on the state before continuing with the error. So you only get this error as a side effect from the body, but you do not get a state that comes halfway from halfway through the body. So you don't have to undo stuff. This is exceptionally powerful. Actually, it's far better than what you would get in Java or C#. It's more predictable. But again, we simply return whatever came out of temp 4. Yes, and now it's happy. The final case, though, that's again the monster, because what we get here, it's the value of the value, and no, wait a second, what's here? So in this case, we know that temp1 dot kind is left, yes indeed, and we just have this value, and this value is, I don't know, would kind of expect the value to be just the right bit, right? So it should be this one. Yeah, okay. I've messed it up a little bit with I've messed it up a little bit with all of these checks. So let's clean it up. So if temp1.kind is left, then inside the left we check, we return, and otherwise we are in the right side, and this shouldn't be needed anymore. Okay, now, okay, cool. So this is slightly better, and now at this point in this place temp1 is right, and here temp1.kind is left, but temp1.value.kind is going to be right. So let's see if that's the case. temp1.kind is left, and temp1.value.kind is right. Very good. Okay. So temp1.value.value, let's call it temp2 here as well. Temp2 is now it's now the recursive case, and now we have no idea whether or not we're supposed to, well, continue, because this is the continuation of the body. The body hasn't failed yet, but it might, and if it does, we want to catch. So what do we do? Well, this cofun here, we could make a coroutine out of it, or we could just call this whatever we want. So let's say that we, let's try the way of making a coroutine out of it. So we map this pair, and we have the cofun, SEA, and obviously the state, and we want to get a full-blown coroutine out of it. How do we go from cofun to coroutine? Well, it's very easy. We call co from fun. And how do we get a state from a state? That's obviously the identity. Okay, and we're reasonably happy. Then let's call this on temp2, and what we get here in temp3 is a pair of coroutine SEA S. Okay, now we could say, okay, you know what? We have this coroutine SEA. Let's call try catch on it with the on error next to it. So temp4, let's see. So I simply want to go from coroutine to coroutine. So it's again map there, but it's not going to change the type. It literally goes from coroutine to coroutine, and here we have a function that takes as input, well, the first coroutine, we'll call it whatever, P, and we call the right catch on P and on error. The right side, still the identity. And we call this on temp3. So now temp4 is, oh look, again, a pair of coroutine SEAS, but now this new coroutine comes out of try catch. So it's the proper coroutine that is capable of try catching, it's capable of managing errors in the first item, and has a state. Now, oops, sorry, now we extract, so we reverse this. We extract the cofun from the coroutine, because now we want to apply it. So it's from co, and I give it temp4. And now temp5 is a pair cofun SEAS. And the last thing I do is I simply apply temp5. Because this takes the cofun, puts the state, and gets whatever result came out of it. But this cofun we have here is the result of applying try catch. I notice that this thing is recursive, but it's not going to be stuck in the recursion because it only calls try catch here, which is after you give the state. So you have to give the state, and there has to happen plenty of stuff before you actually call try catch recursively. Now, again, there is a way, but I'm really going to leave this as an exercise to the reader. These are all things that we can do with a mix of map either and our additional utility function, this thingy here, which again we called collapse either, or it's a visitor variation. It's really the same. Okay. Now there is one operator that we really need, the so-called suspension operator. And the suspension operator is an operator that simply takes a break in the coroutine. So it's very similar to unit, but I want to be able to simply say, you know what, get a state and then take a break and return that state. So don't do anything with the state, but just and after that you simply stop. So it's a coroutine that does nothing, but just takes one step of a break. And let's see, where are you? Where's unit coroutine? Yes. So this suspend coroutine, it's obviously the most characterizing utility function, suspend coroutine. It doesn't need to take a value actually, because it will return a coroutine of SE unit. And it takes a state. It gives inle because it is not going to fail. But then here, let's be careful with the brackets because I don't want to be fighting against brackets all the time when building this. Okay, so it takes inle, but again, now it goes to the right side of the coroutine. So now inre. Now this inre. Yeah, okay, it gets null exclamation mark, and this inre we can give it. This inre we have to give it. We have to build a pair of the cofun, which is the actual coroutine that's going to stop right away, and the state. The state we have because this thing only takes a break, so we create the pair now where the first element simply unit, and the second element, again, let's go for an exclamation mark. Now it's quite unhappy. Let's see if we do it properly, if it's happy. So let's call unit coroutine over SE, and then we pass it unit as a type, and we give it nothing whatsoever. Very broken. Let's see what kind of error we got. Okay, I don't see any unknown types, so it might simply be that there is something slightly more solidly wrong going on. So let's debug it. And or a bracket issue. Oh. See if we got this lucky. No, we did not. Okay, now, so what I want to be able to return here is the right side of this coroutine here. So what I have to return is the usual, either with the cofun SE unit. SE unit. Okay. So And well, let's isolate the type of this. So our result is supposed to have type, supposed to have this type, either per unit SEA and then per cofun SE unit S. Okay, and it's going to be a left side because we want to have this guy here, obviously, and it's going to be then a right side, and these are the two values we want. So let's try to see what happens if we start putting the right annotations to it, because it's probably annotations that ended up being a bit broken. So the first inle, let's really tell it what it's supposed to give back. First inle, the right side, I can write it directly, whereas the left side, it's this big either with the per unit S, and then the per cofun. I think I see the error we made. Oh, why is it unhappy? What's it missing? Left side of comma operator is unused. Oh. Yes. Okay. Cool. That was a moment of panic. All right. And now I have to provide to inle a value of this type. A value, sorry, of this type. That's what it expects from me. Now I'm going to see if we get lucky enough, because now it should know. Now look, inle now knows that the left side is going to be per unit S, but this is really what we have to provide, and this is what it expects from us. So it expects a pair where the left value, that's indeed the error. The left value is the continuation, and the right value is S. So let's create this type. Now the right value is going to be S0, whereas the first value, let's start with now exclamation mark. The compiler is accepting this at face value, but obviously now what do we put in null? And well, first here, or let's take a look at the inle. So the value of first is going to be this, a cofun of SE unit. Now we would just want to take one single break. So the next step we simply want to be done right away. So we could put here almost unit coroutine SE, and then we give it unit, and we pass it unit. But this is not exactly what we need, because we want the underlying function, that's the cofun, and there you go. And here we are. We can remove this ugliness, and we can go back to pretending that we just wrote this as a one-liner, which we clearly did not. Okay. Now we could say, for example, here in our program that we want to give an insight into what's happening. So I could suspend the coroutine. And I have to tell it what the state is, and that's memory and error. Again, we are asking really a lot of the type inference of TypeScript. And now you can see that wherever we want, we can say, okay, you know what, instead of just running to the conclusion, I want my program to take some breaks. And if we were to take my hello world and just give it a state, we give it the first memory, and what we get is a suspension. And we have to call it again. We get the new state, and in the new state, well, there is X, which is either 0 or whatever we put into it. Or we could say, okay, you know what, I don't want to see all the temporary results. Let's not exaggerate. I want to only see one of these results, you know. And yeah, okay. No. Why is number? And well, by doing this, I'm simply stating, okay, after you force the variables x and y to 0 and 1, then take a break so that we can inspect what's happening, and after that, just continue. Or we could say, no, let's continue, but then after you've assigned x to the new value, then we want you to stop. Let us see what's happened, and then we let you continue, and so on. or we could say after you're done assigning the values, take another break, etc. And this is so we've built a multi-threaded system basically, because we could have also multiple coroutines running in parallel. We could define something that has two coroutines and runs the first one until the suspension, then runs the second one until its suspension, and resumes them so that they can kind of go one step until they get to the final result. And the developer is able to control exactly what happens when their threads get suspended and when the scheduler gets to see these suspensions. And now I'm barely scratching the surface of all the things you can do with coroutines. And coroutines actually give you an immense amount of power, because they literally allow you to decide how your program is going to manage state transitions, how it's going to manage errors, how it's going to manage suspensions, and how it's going to manage time. And the moment you are able to build your own framework of coroutines, then as a developer, there's really nothing that can stop you. All right, so this concludes our foray into coroutines. I'm also still quite amazed by the ability of the language to support us, even though it's clearly less powerful than, say, an F# or a Haskell, where we would have gotten a bit more support. But it's also nice to see that these things are applicable to modern mainstream languages, because it's kind of arguable that F# and Haskell are mainstream languages. Actually, no, it's not arguable, they just are not. And it's also nice to see that a pattern like this very clearly resembles patterns like promises in the web development world, these are powerful patterns, and the ability to take control over them is an exceptionally powerful step. Thanks a lot for following this so far, and until next time.